Hey guys, it's Sam for Digital Meet again, and we're going to be looking at Realflow 2.0 for Cinema 4D. So it's actually important to note that I'm using Realflow 2.0 and not 1.0. So there will be some differences between the two. And in this one, we're going to be looking at the Viscous Solver in Realflow 2.0. So let's just get straight into it. So, as usual, I've got a scene here. You probably recognise it from previous tutorials if you've been watching them. I've just got a container that I've made in a scene, and that's pretty much it. I mean, I've got some lighting in there, and I've bent a plane for this backdrop here, but that's about it. So let's get into the guts of this. So I'm going to go into the Realflow menu. I'm going to create an emitter, in this case a circle emitter, and that's going to create that there in the middle for us. I'm just going to drag this up, and my Realflow, as you can see there, my Realflow scene is actually on the floor, and that's why it's not visible. But I'm going to pull the emitter up, and as usual, what I'm going to do is make some changes to my scene slightly. So I'm going to go into scene, I'm going to go to the solver, and I'm going to say use GPU, and I'm going to choose one of my graphics cards there. And just so it helps you guys, I'm going to go to my fluid, go to display, and I'm going to make my particle size a lot bigger. Let's go to 4 and see if that helps. I'm just going to press play, and that seems to be working okay for the time being. So there we have it. And I'm going to add some gravity to my scene as well, because as you can see at the moment the particles are falling quite slowly. So let's go and do that. Realflow, demons, and gravity. And the value we've got in there is 981 centimeters, and that's actually Earth's gravity there. So now it's falling a lot quicker. But we need it to collide with our container. So I'm going to go to our container, I'm going to right click, and I'm going to go to Realflow tags and say collider. So that adds a collider tag. I'm going to leave all these values as is at the moment, and we're just going to press play, and we should be getting some collision there. And I don't think we've got any bleeding through the floor. No particles. Let me just rewind to the beginning just to make sure there's nothing falling through. So, we've got a few dropping off there, but what I'm going to do is just to make sure that there's no particles that are going to escape this and cause us problems with the calculation, because if they do escape, they'll be falling out of this forever, which is something that we don't want. So what I will be doing is creating a kill volume. So if you go to Realflow, demons, and then we've got K volume, our kill volume. So there's our volume where particles will be killed off. So I'm just going to drag this up slightly. So anything outside of this will die. So let's go into our side view, just so we can get things set up properly. I'm just going to pull this right out to the edge. I think we need to do that in all... No, it did it all in all directions, so that's fine. So let's just line that up with this. Pull this up like that. We could probably make this smaller, actually. There we go. So anything outside of that volume now will die. And if I go to the front view, we can just pull this in like this. And if I go back to my scene, we can see now we've got our sort of volume that everything should live in. I'm just going to hide that. I'm just going to press this so it's not visible in the editor, because it can be quite distracting. So that should do what we need it to do now. Yeah, that's filling up nicely. And if I go underneath, anything that's escaping, you saw a couple escape there and it got killed off. So that's great. That's exactly what we want. Okay. So what else do I need? I think I'm going to pull this emitter up even more, actually, up to something like this, just so it's got a little bit further to fall. And I'm going to put another object in to make our interactions a little bit more interesting. Now, there is one thing that I want to go over with this container. As before, in Realflow 1.0, in the collider tag, you'd be able to set the cell size and all that kind of thing. Now, if you look through this collider tag, you'll be going, right, I've got my fluid linked, I've got the enable collision, and I've got all my properties that I can change, like the friction and the bounce and the stickiness of the surface, all that kind of stuff. But I don't seem to be able to find the collision geometry. And if I turn collision geometry on here, and then rewind and play, it doesn't seem to be... what's going on there? It's a little bit weird. And that's because in Realflow 2.0, they've broken out the what used to be the collision tag in 1.0 to two different tags in 2.0. So if I select my container and right click again, go to Realflow tags, we've got this volume tag now. So if we hit that, and there we go, there's all our cell sizes and all that kind of thing. So let's go back to our collision tag, say show collision geometry, rewind, go to this, and I'm not sure why it's doing that. I think it might be because I've got ambient occlusion on, I'm guessing. No, that's not the problem. Well, that is slightly weird, isn't it? Okay, that is strange. It might be the lighting, maybe, I'm not sure. But the collision geometry detail is medium in our case. So if I turn this off and turn this to, I don't know, something low like 10, and then rewind, there we go. It might be because the... let's have a look. Let's go to our scene and just turn off the lights for a minute and just see if that actually makes it. There we go. We can see our collision geometry now. So that has obviously been affected by our lighting. So if we turn this back to auto and then go back to the beginning and play, it should regenerate. And that's what our collision geometry looks like. So I'm actually going to make this a little bit more... turn that to 10, just so it's a little bit more closer to what we want. And we actually want it to be, it says volume mode, solid inside, and I actually want this to be some kind of shell, so it actually shells the entire object. There we go. And as we can see now, that's what our geometry looks like. I wonder what it looks like with auto turned back on, if it's any better. No, it's actually even bigger. So let's turn this off and let's make our cell size a little bit more smaller and see if that helps. So let's make it 5 centimeters and rewind. That's a little bit closer to the real deal. Okay, well that should do us, I think. And also this domain offset, surface offset, it says 10 centimeters. Let's make this smaller, 5. There we go, it's a little bit tighter now. So now, if we go back to our collision geometry and turn that off, yeah, it looks like everything's working as it should be. Okay, so, right, this tutorial is not really about this collision geometry, so that was just like a little side note, really. So we'll keep that as is at the moment. We'll close up the scene and turn our lights back on, just so it looks nice. And we'll close this back up. And we're back to where we need to be. Okay, so viscosity. I'm just going to save it here, just in case we have any problems. So, viscosity. Now, I think in Realflow 1.0, it was actually... I think if you went to fluid and then this, you'd actually have a viscosity slider somewhere along here. Now, don't quote me on that, but I'm pretty sure that was in here somewhere for this solver, but I could be wrong. It's just that I can't look at it because you can't have two different versions of the plugin installed, and I've got 2.0 in at the moment. But the viscosity is a different solver now. So if we choose the fluid that's associated with our emitter, and it's associated with it because when you create it, it creates a fluid for you, and when you create any daemons, it automatically detects the fluid that should be going in there if there's one in the scene and puts it in there. So this is the fluid we're dealing with. There's only one. So viscosity. Like I said, I wanted something a bit more interesting to interact with. So I don't know, let's grab a platonic. That should help us. And I'm just going to put it here. And obviously you can see that this is not being interacted with. And that is because we need to actually make it collidable. In fact, I wonder if I can just copy these tags. I'm not sure you can actually do this. So let's find out, shall we? Seems to be working. So now we can see our particles are interacting with our platonic object as well. Anything that gets flung over the side, don't worry about too much because they're getting destroyed. Okay, so that's all very well and good. So let's get onto our viscosity then. Now it's actually a different solver. So if we go to the fluid, we can see that we've got this liquid PBD. And you're probably thinking, I don't know what that means. Right, okay, so the liquid PBD is a very fast fluid type. So it's very fast to solve. You've got a different one above it actually, SPH, which is a very accurate fluid solver, but not as fast as the default one. And you can see a few other options here. Dumb, it just means the particles are often used for spray or foam. They can't react with each other. They don't have the characteristic fluid properties, but they're animated really, really fast. So, but now you can see that we got these options: granular, viscous, viscoelastic. And we're going to be dealing with viscous today. So let's choose viscous. And that opens up a load of possibilities for us. But I'm just going to play it actually. In fact, I'm going to put our red material on our platonic as well. And then we can see what's going on with this. Oop. And there you go. You can see it all clumping up there. And like it says on the tin, it's viscous. And you can see that it's taken a little bit longer than normal to have a think about what's going on there. So what can we do with this? Let's have a look at our settings then. Let's go back to our fluid and let's go through some of these and actually find out, what's going on. So we've got the links in here. We don't need to worry about that. We changed our type to viscous. And the next thing that we should look at really is the resolution. So you probably come across the resolution before when it comes to fluids. In fact, when we've been on this one, I think the resolution is a description of sort of how closely the particles are tied together, actually. So if we actually upped our resolution in this mode to say something like 5, you can see that there's a lot more particles in a lot smaller space. And that usually gives us a sort of better, more accurate solves and that kind of thing. So I should imagine it does the same thing when we have a look at viscous. So what's this by default? This is 2. Okay, so with this setting you can change the amount of particles or resolution, and it depends on scene scale and emitter scale. But it also affects the fluid's mass and therefore depends on density too. So with the resolution set to 1, a volume of 1 meter by 1 meter by 1 meter, so 1 meter cubed, is filled with 1,000 particles. So at a resolution of 2, obviously a volume of 1 meter cubed is filled with 2,000 particles, and so on. So if we just play this at 2, we get this blub 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 blub. Lovely. So that's what we get. But if I crank this up to 5 and do the same thing, we can see that there's a lot more particles in the same space, and therefore we'll probably get a better solve, a better description of what's going on. So that's pretty much what that does, and you can see that it's chugging away there. In fact, let me just check that my scene is actually set up to use my graphics card, and it is. So you can see that it's a bit more of a complicated solve going on there. Okay, so there's that setting. Let's get back to our fluid. Density. This parameter is defined as mass per volume unit and is different for each substance. Density does not change the fluid's behaviour, but it's possible to mix fluids from different domains. So you might have one fluid in one domain that is I don't know, got the same density as water. So oil and water is a good example. The reason oil floats on top of water is because it's less dense than water. Pardon me. So you can simulate substances like oil and water. The unit is kilograms per cubic meter. So the density of water is usually 1,000 kilograms per cubic meter, and that's usually just written 1,000 kg slash M3. So I've actually got a chart here, so we can see that water here. So I just looked up, fluid densities, and it says here water pure, and you can see here where it says 1,000. This column's temperature, and I think this column's density, and that's kilograms. Oh, excuse me. I don't really want to get into the technical jargon of this, but it's pretty important if you want to simulate this kind of thing. So the density is kilograms per cubic meter, and as you can see at the bottom it says 1,000 for pure water. So water is 1,000, and if we look at something like oil, I don't know, let's have a look. Oil, lubricating oil, 900. So it's less dense, and therefore it will float on top. So that's the point of the density. Density here. So I don't think there's actually going to be too much difference if I leave it at 1,000 and do this. Oh yeah, that's great, brilliant. And if I rewind it and say the density is 500, I don't think we're going to actually see a lot of difference. No, we're not. It's just for when fluids are interacting. So if you're playing around with that value and not much is happening, that's why. It's more to do with the way that fluids sort of react to each other. So I've Control Z'd that. It's back at 1,000. Okay, next we've got the internal pressure. It goes from 0 to 1. So there's no negative values there, obviously. And it simulates the forces between nearby particles and pushes them apart. This makes the fluid fill a greater volume. So, the clue's in the name, internal pressure. External pressure, you can imagine that as an atmospheric pressure. So the reason that your blood doesn't escape, bulge through trying to escape your body is because the external pressure of the atmosphere pushing back is what sort of counterbalances that. So again, this parameter goes from 0 to 1 and tries to limit a fluid's expansion. So it's kind of like dampening really for the internal pressure, if you like. And it's comparable to atmospheric pressure. So the higher this value is, the more particles tend to stick together and that kind of thing. Also, the substeps and iteration settings in the Scene Node Solver tab influence how this parameter acts on the fluid. So if we've got an external pressure of this, we can actually go to the scene, go to the solver, and you've got these auto parameters. But if we turn this off, we can actually affect some of these. So you can mess with the substeps and the iterations. A lot like the dynamics that are built into Cinema 4D. If you find that something's not interacting quite right, it's not resting, or it's going through the floor, you can whack up the substeps and the iterations, and you tend to get a more accurate solve. And that's probably the same kind of thing that's going on here. It's adding substeps to each frame of the calculation. Okay, back to the fluid. Okay, tensile strength. So higher settings increase a fluid's tendency to contract and form string-like structures. As a side effect, the fluid's borders become thicker. So again, it's got a value of between 0 and 1. So let's just play this out and see. In fact, let's reduce the viscosity, because you can see here. In fact, that's the setting afterwards. So let's talk about that first. Viscosity. This parameter lets you create substances like cream, chocolate, honey, toothpaste, that kind of thing. And the viscosity ranges between 0 and 1 and can be animated. So you can actually have it at 0, and you can actually animate this getting thicker by using this little node there. Okay, so it could be 0, shoot up to 1. So that's pretty cool. So I'm just going to give this a viscosity of 0.5, and this should run quicker than it was running a minute ago. Yeah, it's a bit more runny. So you can really control, you know, if you think, well, I want this to be more like warmed up chocolate, you can say maybe 0.25. So it's got a bit of, so there we go. So it's a bit more runny. I'd say that's warmed up chocolate would probably be a little bit runnier than that, to be honest. So let's go 0.15. So maybe something like that. Ooh, that's proper gloopy. Bloop. Nice. Okay, so now we've got something like that going on. Let's move back to the tensile strength. So as I said before, it increases the fluid's tendency to contract and form string-like structures, and the fluid's borders become thicker. So now that we've got our viscosity sorted out, let's have a look at the difference between this. Okay, I mean, it is looking like stringy structures already, but the likelihood of that happening with this will go up when we whack this up. So let's put the tensile strength right up and see how that affects our fluid. Seems like there's a bit more resistance in it as well. Yeah, and we can see that it has actually changed. It tend to sort of clump together, whereas before we were getting a lot more action like this. But over here we're seeing that it's tending to sort of stay together and you know, drag it down with it. It's a lot more like syrupy, I suppose. So that's the tensile strength. So let's just stop that and put it back to what it was. Okay, the next thing on our list is cohesion. So this is a force of attraction between nearby particles. So with particle streams, you will get a look similar to toothpaste or thick paint coming out of a tube. And again, values from 0 to 1 are accepted. And again, substeps and iterations actually play a part in this and influence how this parameter acts on the particles. So again, let's have a little look at what we've got at the moment. Okay, blah, 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 blah. Okay, so that's all sticking together quite nicely, and that's what we got. So now let's whack the cohesion right up and see what we get. Oh yeah, okay. So I think I might have gone a little bit overboard there with the cohesion. Let's whack it down to, what was it originally? 0. So let's put it up to 0.5. Even type that in. So that's pretty clever. That's pretty clever stuff. So yeah, it's definitely taken a lot longer to slide down the sides there, and we can see that particles are being attracted to each other, like they're in clumps. Okay, that is good. That is clever. So you could see how that would be really useful when trying to create a very specific type of fluid. Let's get back up here then. In fact, I'm going to turn the cohesion up. Let's get it to 0.75, something like that. So it still moves away from our emitter, but there we go. So you can see how the particles have really, well, does what it says on the tin, doesn't it, really? The particles are attracted to each other, they're tending to clump together. It kind of reminds me of protein strands that, you know, tend to clog and coagulate together. Kind of like frying an egg. You know, the protein starts to clump together and as it goes white, and yeah, okay, that's very cool. Kind of like scrambled egg, you keep it moving, and as it heats up, you know, these fibrous strands start to form and it starts to clump together, and yeah, okay. I'll stop banging on about food now, shall I? Right, so that's the cohesion. Let's reset that to default. We also have cohesion, that's what I was looking at. Damping. So damping smooths the relative velocities between nearby particles. So a small amount of damping helps to stabilize the simulation, while higher values introduce more viscosity to the material. Again, the range goes from 0 to 10. So, you know, they've said there that a small value, it will smooth out the velocities between particles. So if you've got a particle moving really quickly and next to a particle that isn't, it will kind of average them out and smooth them out, if you like. So again, let's take a look at our simulation as normal. I might just drop that down a little bit more as well, so 0.1, just so it moves a little quicker. And we can have a look at that simulation. Very gloopy, very nice. You go blub, 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 blub. Okay, cool. Now let's have a look at our dampening. If we crank that right up to 5, what are we going to get? Well, it did say that it would introduce more viscosity into our scene. And it looks like it could have. These streams at the side definitely seem to be different than they were before. But again, it's a smoothness setting for the velocity, so we can reset that to default. Okay, compute vorticity. We've got this checkbox on and off. Now, I've got a horrible feeling that when I turn this on, so again, this is what we've got. I've got a horrible feeling that when we turn this on, it might even choke my scene to death. But let's have a look, shall we? It's actually not too bad. But largely this setting is unnecessary, because basically vorticity hardly contributes to a fluid's behaviour, and is therefore disabled by default to improve performance. So basically you're just going to get better performance if this is left checked off. But they've put the option in for you to check it on if you want a super accurate solve, and so you have to activate this option before the simulation starts if you need it for filtering or shading purposes, something like that. But by and large, you're not going to need that. Okay, so next setting we've got max particles, which, you know, it's pretty obvious when you think about it. But what you can do is you can enter a value to stop emission at a certain amount of particles. So it's based on the total amount of emitted particles. And it's important to note that, because let's just drop this down to something stupid. In fact, can I actually reset that to default? Okay, so let me put this at 1,000 particles, because that is a ridiculous amount. Okay, there you go, 1,000 particles, and then it will stop emitting. So let's put this up to something like 5,000 particles then, just so we have a little bit more in the scene. Right, so it's primarily dealing with the particles emitted. So you should be very wary of this setting if you've got kill volumes. Okay, so, and the reason I bring this up is because this is based on the total amount of emitted particles, it isn't, you know, it may not play nice if you're killing particles off. So say you've got 50,000 particles, you know, let's say you put 5,000 particles here, like I've done, and there are currently there's currently 1,000 particles in the scene, but I've already killed 4,000 particles off. This will stop emitting after 1,000 particles, and you'll be thinking, well, I put 5,000 in and there's only 1,000 there, and it's because you've killed off the other 4,000, and it does not take them into account. So just be warned that this, you know, it basically ignores, it doesn't sort of go, oh, well, he's killed off a load of particles, so now we can crap some more into the scene. It doesn't work like that. It looks at the total emitted. So that's just something to bear in mind. Create initial state. I'm sure you've all come across this before, so I'm going to actually reset my max particles to a default value and play this again. So say I've got to this stage and I've gone, oh, that's lovely. Or even better, let's actually put 10,000 particles in here actually, just so it craps out 10,000 particles. Blah, 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 blah. There we go. And let's say I want this to be my initial state. I can press this create initial state button, and that's created an initial state. And if I rewind now, you go, right, well, it's disappeared, and oh, it's just simulating again. And it's because I'm not using my initial state. So I've created one, but you've got this little checkbox, use initial state, which I've put on there now. And there we go. It starts from where I created my initial state. So it stores the location of all the particles and their velocities and all that kind of stuff. So you can start from anywhere within that simulation you like. So that about covers it really for the Viscous Solver. I just wanted to go through some of the settings there for you. So you can get a nice viscous fluid, and you can really use these settings here to tailor the kind of fluid that the look that you want for it. So I think my next Realflow tutorial, we've gone over quite a lot of I mean, there's more to do when it comes to particle sims and all that stuff, but we haven't actually meshed anything yet. So we've got lots of scenes where we're looking at particles like this, but we haven't done anything to do with the meshings, and therefore rendering materials, that kind of stuff. So I think it'll be good to get into the meshing side of it. And a lot of the new features in Realflow 2.0. There's a lot of stuff you can do now. Rigid bodies, going into fluids, buoyancy, all kind of cool, funky physics stuff. So I think we better get into that as well. As always, guys, check out the website, digitalmeat.uk. There you can vote for the next upcoming tutorials. There's a poll there, and that's pretty much what I go by. Also, don't forget to follow me on social media. You can find links to that those in the description of this video. So I'm on Facebook, Google Plus, and Twitter. So hit me up there. And I've got a Patreon as well. There'll be a link up at the end of this video on the outro. So you can become a patron, and you can get some free downloads and Patreon exclusive content. All right, guys, I'll see you next time. Bye.